In this video, we will look at the concepts of conservative forces and potential energy. To understand conservative forces, we need to look at a cyclic process. Our first example will involve a mass on a spring. So what is a cyclic process? A cyclic process is one where the system starts and ends in the same state, in the same configuration. So let's say we have a mass, m, attached to a spring of spring constant k. It is on a frictionless floor and the spring is attached to a wall. Initially, the spring is at its natural length, so it's neither stretched nor compressed. And in this position, the mass is at the origin. Now we apply a force and we move the mass, and so since the mass is connected to the spring stretches, and we move it by a distance d. Now naturally there will be tension in the spring and it is trying to pull it backward, so there will be some force of the spring on the box and there's the applied force on the box, and the two of them will balance out and they're holding it steady right now at a distance d. And because the net acceleration is zero, the magnitudes of these two forces must be the same. And we know from Hooke's law that the magnitude of the spring force will be the spring constant k times the distance d. So we have F applied is equal to kd. Now remember, these might have the same magnitude and opposite directions, these forces, but they're not an action-reaction pair because they are both acting on the box. And action-reaction pairs of forces never both act on the same thing. If one is B on A, then the other is A on B. So this does not apply here. Okay, they're just two forces that balance out. Okay, so the net force on the mass is zero and it is at rest. Okay, and what we're going to do is we're going to remove the external force, F applied, so that the only horizontal force acting on the mass is the spring force. There's still the normal force and gravity, but those aren't going to change with time, so we'll ignore them for the time being and just focus on the spring force and the behavior of the mass. So this is our starting configuration. We've just let go of the block. Its velocity is still zero, but the spring force is acting, so that is not going to stay at velocity zero. Okay, so the spring force is acting, and so it starts accelerating the block to the left. All right, it's trying to pull it back to the equilibrium position, because we know that once the block is back at x equals 0, the spring will no longer be stretched, and so there won't be a spring force. Okay, so now we see by this point the mass has reached x equals 0, the spring is no longer stretched, but what we do notice also is that the mass has built up some kinetic energy because the spring has been doing positive work on the mass, because the force was pointed to the left and the displacement of the block was also to the left. It was moving, the velocity was to the left. So since they both point in the same direction, the spring force is doing positive work on the mass, and the mass builds up kinetic energy. And so even though it's reached x equals 0 and there's no more spring force, now that it's at x equals 0, it has already built up some kinetic energy, so it's going to overshoot. Okay, so there's no more acceleration when it's at this point, but it still has a velocity, so it's going to overshoot. Alright, so the block has overshot the x equals 0 configuration, and now what's happening? It's still moving to the left, but the spring is now started to get compressed, so it exerts a force on the block to the right. So now the force and the velocity point in opposite directions, and so because there's a 180-degree angle between them, the spring force is doing negative work on the block. And since it's doing negative work, it is robbing the block of kinetic energy. So the block is slowing down until eventually the block comes to a stop. And so one thing we might ask is, okay, where does it come to a stop? And we can figure out that, okay, there's no friction, and so the spring took a distance d to build up a certain amount of kinetic energy, and now it's going to take the same distance d to remove that kinetic energy. Now remember, this is not a constant acceleration case, because we have force of the spring is equal to k times x, right? And so as x changes, f changes, and as f changes, the acceleration changes. So this is not constant acceleration. We will see later on in the course that this is called simple harmonic motion, and the velocity and the position and so on are varying sinusoidally with time. But we can see it makes sense that if it took a distance d to speed up, and it's the same spring that's slowing it down, it's going to again take a distance d. Okay, but it stops here momentarily, but it can't stay like that because there is a net force on the block. The spring is still acting on the block because the spring is now compressed. It's not happy, so it continues to push to the right. It had slowed the block all the way down to 0, but it doesn't stay at velocity equals 0. The acceleration continues, and so it now starts to move back to the right. Okay, so it's moving to the right, and once again it builds up some velocity because now the velocity and the spring force are pointing in the same direction again, and so it builds up kinetic overshoots, and finally the spring starts stretching, and then the spring force and the velocity are in opposite directions, and so it slows down and it comes to a stop, and we see that it has come to a stop in the exact same configuration that it started in. All right, so notice that we have come back to the same position, we have come back to the same velocity, the velocity is 0 again, and we could just keep looping this video, and that's all that this mass on a spring would do, to just keep oscillating back and forth like this. So we have gone through one whole cycle here, right? We have started here, gone all the way here, come all the way back. And if we continue playing the video, then it's just going to repeat the same motion again and again. So we have completed one whole cycle, we have come back to the starting point, same position, same velocity. And now we can ask, how much work did the spring force do in total? Well, what we see is that during this quarter, when it was moving in from the extreme position to the middle of the oscillation, right, at x equals 0, during that time, the velocity and the spring force were in the same direction, so the spring was doing positive work on the block. During this quarter, the spring was getting compressed, so the block was moving to the left, but the spring force was to the right, so it was doing negative work. During this quarter, the two of them were pointing in the same direction again, so it was doing positive work. And then during this quarter, they were pointing in opposite directions, so it was doing negative work. And you can crunch the numbers, and you will see that the total work done by the spring force, if we look at one complete cycle, the total work done by the spring force is 0. Okay, so that's one example of a cyclic process. Let's look at another example of a cyclic process. So let's say I have a book of mass m, it's initially at rest, and I push on it, and so it picks up speed and reaches a speed v. But it is sliding on a table, and there is friction. Let's say there is kinetic friction between the book and the table. All right, so I was pushing it, I push it a distance d. Okay, so it starts at rest, and I push it, and it picks up speed, it reaches speed v, and then I push so that it starts slowing down, and it comes to a stop, and it's moved a distance d in the positive x direction. And then I start pushing to the left, and it starts picking up speed going to the left, and then again I change the way I push so that it starts slowing down, and then I bring it back to the starting position and it's at rest again. So this is another cycle, right? I started with the book at rest at a certain position, and at the end of the cycle the book is back to the same position and the velocity is zero again. So the system has returned to its initial configuration, right? The same position, same velocity, all of that. Uh, so the system has completed one whole cycle. So now, what about the work done by the force of friction? Well, we can see that as the book slides, the force of friction, of kinetic friction, is always pointing, in this case, in the opposite direction to the book's motion. So it's doing negative work. And that applies when it's moving to the right and also when it's moving to the left, right? The friction is always, in this case, pointing in the opposite direction to the motion of the book. So throughout this cycle, kinetic friction was doing negative work on the book. So in this example of a cyclic process, the system has come back to the start, but the total work done by friction is not zero, it's negative. Well, it's non-zero is the important thing. And we can calculate how much the work done is, because we know that for a constant force, uh, we can just use F dot D to find the work. So what we do in this case is we consider when the book is moving to the right as the first half, and so the force of friction is constant and it's pointing to the left, the displacement is to the right, and so we do F dot D and we get minus mu k mgd, right? Because mu k times n will give us the force of kinetic friction, and in this case, because it's a horizontal table, then n is equal to mg, and the distance moved in this case is d, so we get mu k mgd, and we get a minus sign because the angle between the force of friction and the displacement is 180 degrees. Alright, so that covers one half, and then we move the book back to the left and we do the same amount of work. We again get a minus mu k mgd, and so the total amount of work done is minus 2 mu k mgd. But the important point is it is not zero. Okay, let's consider one more example. We will look at a pendulum, right, which is basically just a mass m attached to a string of some length L. And let's say that we pull it back. All right, so it starts at some angle theta naught, and we then release it, and well, once we release it, it starts swinging down. And so right now it's completed a quarter of an oscillation. It's gone from the extreme position over here to the middle. So what are the forces acting on the bob? There's the force of gravity and there's the force of tension. How much work does the force of gravity do on the bob? Well, let's focus on the sign. We know that the force of gravity is pointing down and the displacement is like this. And at each point, we see that the angle between the force of gravity and the velocity is less than 90 degrees. So that means it is the force of gravity is helping speed up the bob, and so it's doing positive work on the bob. What about the work done by the force of tension? Well, for the tension, we know that the tension, if that's along the string, the velocity is perpendicular to the string, and so there's a 90-degree angle between the tension and the velocity, and so the work done by the force of tension is 0, because cosine of 90 degrees is 0. And remember, when you're calculating the work, you take a dot product between the force and the displacement. Okay, so we saw that during the first quarter of the oscillation, the force of gravity does positive work on the pendulum, right? And then during the second quarter, uh, the velocity and the force of gravity have an angle greater than 90 degrees between them. We can see that if we draw it out. Force of gravity is acting down like this, but the velocity would be like this, and so we see that the angle between the force and the velocity is greater than 90 degrees, and so the force of gravity does negative work on the pendulum as it swings up in the second quarter, and then as it swings back down in the third quarter, it is doing positive work again, and then back up again in the fourth quarter, and force of gravity is doing negative work there, and so it's back to its starting position, is back to rest where it started, and the work done by gravity over an entire cycle, an entire oscillation, we can see that that will be zero. And of course, the force of tension throughout does a work of zero. But what we're interested in is types of forces like gravity and the spring force, where it's not always zero work, but sometimes it does positive work, sometimes it does negative work. But if you do a complete cycle, then the total amount of work done on the system is zero. So those are two we've seen. In some, like the pendulum or in the spring mass case, we see that the amount of work done on the system is zero, right? The net work done on the system is zero. And these kind of forces, like the spring force or like gravitational force, these forces we call conservative forces. Okay, so what is a conservative force? One way of defining them is it is a force that when it acts on a system in a cyclical process, then after one cycle, the total amount of work done is zero. And it sounds like a very arcane definition, and like, why is this of interest? But we'll see why this is of interest. And the other case that we saw was we had a system that went through an entire cycle, but there was a force acting on the system that did some non-zero work. And these are non-conservative forces, and the most common examples we will see are friction and the drag force. So, conservative forces are important for two reasons. We can associate a potential energy with each conservative force. So, along with gravity, which is a conservative force, we can associate gravitational potential energy. And along with the spring force, which is a conservative force, we can associate a spring potential energy. And similarly, once you go on into other courses, you can see that the electrostatic force is also a conservative force, and so there's an electrostatic potential energy, and so on. And the other reason why conservative forces are important is that the work done by a conservative force in taking the system from some initial configuration to some final configuration, it only depends on the starting and ending configurations. It does not depend on the path taken, right? Or like what you do in between. All right, so all you need to know is how did the system start and how did it end, and that will be enough for you to calculate the work done by that force. And so this we call path independence, and that's really useful because instead of doing a very long calculation where you look at the force and how it's changing and how the object is moving bit by bit throughout, you just look at how did it start, how did it end. That's enough. So to give an example of that, using gravitational potential energy, let's say I want to take this ball from here and I want to take it to the top. There are many different ways I could do it. I could take the ball up in a helicopter and drop it off on the top of the hill. I could just roll the ball straight up the hill. I could roll it up the hill but take a really long and winding path. All these are perfectly valid ways. And if in each of these cases I calculate the work done by the gravitational force, well, how can I do that? Well, we know that work is integral f dot dx from initial to final. But we know that if the force that is acting is a constant force, we can simplify this into just f dot d. And the gravitational force is a constant force, so let's go ahead and use f dot d. Oh, and one more thing. Notice that the total displacement of the ball is a distance s in the x direction and a distance h in the positive y direction. Okay, so we're using work is equal to f dot d for a constant force. Our displacement vector in this case is si hat plus h j hat. And so when we carry out the calculation, notice that the force is the gravitational force, which is minus mg j hat. We do a dot product with d, which is si hat plus h j hat. Well, we know that j dot I is 0 and that j dot j is 1. And so it simplifies to just minus mgh. That is the work done by the gravitational force. And this makes sense. The work done by the gravitational force in this case is negative because the ball is being moved up, but the gravitational force points down, so they point in opposite directions, and so the work done is negative. Okay, but here's the important thing. This result applied for all those ways of taking the ball up. It didn't matter whether you just rolled it straight up or took it through a helicopter or used a really long winding path. All that mattered in the end was the initial height and the final height. Okay, and the difference between them actually was all that mattered. And that is all that comes into this expression for the work. So in every case, we get minus mgh as the work done. Since the displacement along the force of gravity, that is the displacement in the y direction, is the same in every case. However, if we looked at the work done by friction in each of those cases, it would be different. Right? It would be different in each case, and this plays along with friction being a non-conservative force. It is not path independent. The path that you take does matter to calculate the work done by friction. But since gravity is a conservative force, the work that it does is path independent, and all you need to know is where you start and where you end. And this is also another way of saying that if the work done is path independent and all you need to know is where you start and where you end, if you end at the same place that you start, then the work done has to be 0 for a conservative force. Right? Because it doesn't matter whether you were just staying at the same spot all the time doing nothing, or whether you went out and came back. In either case, the work done has to be the same for a conservative force because of path independence. And so the net work has to be 0. That's the only answer that makes sense. Okay, so now that we know how to distinguish between conservative forces and non-conservative forces, let's look at some of the potential energies associated with these forces. All right, so this is pretty much just a definition, but it turns out that the work done by a conservative force, okay, so let me just put CON as conservative here as a reminder. The work done by a conservative force is equal to negative delta U. Okay, so right now that's a little vague, so let's emphasize that. The work done by some conservative force F is negative delta U for the same force F. All right, so in other words, if we're talking about gravity over here, has to be gravity over here. Okay, so work done by gravity would be negative delta U of gravity. Similarly, work done by the spring would be negative delta U of the spring. But in general, we would not have work done by gravity is equal to negative delta U spring. This would never happen, right? They have to be the same force on either side. I mean, this could happen by accident in some particular situations, but not as a general relationship. These are general relationships. Okay, so let's look at this more closely. We know that the work done by gravity, since gravity is a constant force, we can do F dot D. And so we have minus mg j hat, that's the force of gravity, dotted with D is the displacement, so it's final position minus initial position. And the final position can be written as x final I hat plus y final j hat. Initial position as x initial I hat plus y initial j hat. And we, can distribute the minus signs and then do the dot product. And we know that only the j hat with j hat term will survive, and so our final answer is minus mg times y final minus y initial. Okay, so this is the result we just calculated. But we said that W gravity should also be equal to negative delta U gravity, and delta U is simply U final minus U initial. So since these are both equal to W gravity, let me compare these two. So I have this is equal to this. Let me distribute that mg inside. So I have minus parentheses, and then I have mg y final minus mg y initial. Here I have minus parentheses u final minus u initial. So if I compare them, well, I see a pattern, don't I? I realize u initial is equal to mgy initial, and u final is equal to mgy final. Or in other words, if I'm looking for a potential function, I just have potential energy due to gravity is equal to mgy. So this is how we came up with that formula mgh or mgy for the potential energy due to gravity. We didn't just arbitrarily make it. It came from that definition that the work done by a conservative force had to be negative of delta U, right, for the potential energy associated with that conservative force. All right, let's try it for the spring force. So if you've been reading the textbook, you would have seen that the work done by the spring force is 1/2 k parentheses x initial squared minus x final squared. All right. But we also have work done by the spring force, since it's conservative, would be negative delta U spring. And once again, we write that out as negative parentheses U final minus U initial parentheses closed. Okay, and so now we compare these. And we want to compare them, so we want to have that same minus parentheses structure. So we pull out a minus sign here and we flip the order. So it's now x final squared minus x initial squared, but there's a minus sign outside. And so if we compare them now, we can distribute the 1/2 k inside the parentheses. But if we compare them now, we see that u initial is 1/2 k x initial squared and u final is 1/2 k x final squared. Or if we just generalize, then we have simply in general potential energy of the spring is 1/2 k x squared. All right, so that is our expression for the potential energy of the spring. So these are the two main potential energies we'll see, the gravitational potential energy and the spring potential energy. Since there's more than one kind, you should specify whenever you're writing your solution to a problem, you should specify which potential energy you're dealing with. And that's it for this lecture. In the next lecture, we will look at conservation of energy and solve a few problems. From this lecture, the main takeaways are the ideas of conservative and non-conservative forces, path independence, and the relationship between the work done by a conservative force and the potential energy change. Right? So remember that the relationship is, work is equal to negative delta U. And so if you know one side, then you can figure out the other side. But again, remember that this only holds for conservative forces, right? Such as the spring force or the gravitational force. Okay, that's all for this video. I'll see you in the next.